Okay, so now we look at the Fourier expansion of the potential S, and it's straightforward mathematics. As I write the Fourier expansion, I write it like this, and pay attention that I am not writing this x alpha in terms of sk. I have reserved sk for something else. I am writing this in terms of qk. Why? Because if you take the gradient of s so that you get vector s, and then let's say that for vector s I am writing Fourier expansion like this. For vector s I am using sk in the Fourier amplitude, but here I'm not using sk, here I'm using qk. Let's see, let's pay attention to this part. So when I'm doing Fourier expansion of s, I'm writing sk, and then I use this negative gradient of s. When I apply the negative gradient of s, I come up with this thing. So I get this. So now you see sk is equal to minus ikqk, right? My goal is to write here sk whose dimensions are the same as this vector s. This is what I want to see. This is what I want to achieve. Note that these two are not dimensionally the same. See, this is vector s and this is potential s. Gradient of potential is vector s. So dimensionally, these two are different. And that's why qk dimension is not same as s dimension, vector s dimension. Qk dimension is same as potential s dimensions, but but what I want to achieve is I want to write here sk whose dimensions are same as vector s, not of this potential s, but of vector s, because it is ultimately the vector perturbation we are looking at. So our original quantity is the vector quantity. So how do we get S? We get S from vector perturbation delta F. Delta F is a Euclidean vector that is decomposed into S and V. S we are writing in terms of potential S, but potential S dimensions are not same as the vector S. So if I want to have the potential S vector same as I mean uh, if I want to write if I want to have the amplitude of Sk same as vector s, then I have to wait and not write sk here, because writing sk here means sk, the Fourier component, is not having same unit as vector s. It will have same unit as potential s but not as vector s. So let's write qk here and let's see that how this, and when I'm decomposing vector s, then I'm writing sk. This vector sk is having same unit as vector s. So now let's see how qk and vector sk are related. Qk and vector sk, simply you can see that vector sk is equal to ikqk minus ikqk. So vector sk magnitude is equal to magnitude of kqk, and qk is a scalar. So I can simply write k times absolute value of qk. So this is absolute value of qk. Now you notice that this sk vector has the same unit as this vector s, right? So I can, the magnitude of this vector sk, let me define this sk, scalar sk, whose magnitude is same as magnitude of vector sk. Define a scalar sk whose magnitude is, whose absolute value is same as the magnitude of vector sk. So this subtlety, make sure that you grasp properly. What we are trying to achieve is, what is our goal here? Our goal here is to write this in terms of the Fourier component whose dimensions are not same as S but are same as vector S. That's why we are going through all this jugglery here. because we want to extract sk, we want to derive sk, we want to come up with sk whose dimensions are same as vector s, and that sk is a scalar. So we are trying to come up with a scalar sk whose dimensions are same as this. So what is that scalar sk? We saw that when we decompose vector s like this, and then this vector sk is related to qk in this manner. So now if I define a scalar sk whose absolute value is equal to the magnitude of vector sk, then this scalar sk has the same units as the vector s. And that means how is this scalar sk related to qk? This scalar sk, through all this mathematics, you can see that k times absolute value of qk is equal to absolute value of sk. So what is now sk? Sk is something whose absolute value is k times absolute value of qk. Now I can write qk in terms of sk as long as I honor this equality. As long as I honor this expression, k times absolute value of qk is equal to absolute value of sk. If I honor this expression, I can substitute qk in terms of sk. And you see, from here on, cosmologists follow two conventions because you have some free will here. You have some freedom here. So, because we want to achieve absolute value of qk is equal to absolute value of sk divided by k, right? Or absolute value of sk is equal to k times absolute value of qk. So you see there are two conventions. Convention one is that you write sk like this, and convention two is that you write sk in this manner. And in both cases you see that we are honoring this equality. K times absolute value of qk is absolute value of sk, and this is a convention followed by cosmologists. So if you use this convention, you end up getting this expression. If you use this, and this is simple mathematics here, nothing fancy. So if I use sk is equal to kqk, then you can write vector s like this. So what is vector s? Basically, vector s your becomes, instead of so this vector s, now qk you can write like this, sk over k. So you see the expansion of vector s now becomes this. So we have, so when you are expanding vector s, this sk is related to this sk in this manner. And this is what is convention A. And if you follow convention B, then your vector expansion is this. So it is a matter of personal choice which convention you want to follow. So we will be dealing with vectors, perturbations, and if I can either expand vector like this, that I can write S as Fourier expansion, the Fourier amplitude is minus ak over k times scalar sk, or it is k over k times scalar sk. And what is scalar sk? Scalar sk is nothing but k times this. So what is qk? You can also say that qk is a scalar sk over k, if you like. If you like, you can say, okay, the Fourier amplitude of this Fourier wave is sk over k. That's what it is. So what is qk? Basically this sk over k, and in this case it is sk over minus iota k. So you can follow it. In this case, sk over k here, and vector s will be minus iota k over k sk. So in this case, sk over minus iota k, qk is sk over minus iota k. So this qk is sk over minus iota k, and for the vector one we have k over k, vector k over k sk. So you see both scalar and vector, I mean both potential and original vector perturbations, we are now able to relate via one sk, this. So both expansions we can write in terms of sk. Scalar also we can write in terms of sk, vector also we can write in terms of sk, and this sk is having the same magnitude, same units as the vector sk. As you can see from here, when you are writing vector in terms of this, so sk is having same unit as s, but then sk is related to q via this expression. So we will follow a convention. What we will do is that when we follow a convention, we get this. So this is followed by convention A is followed by Lederleth and the notes published by Helsinki University, and convention B is followed by Scott Doddleson. But we will follow convention A, and convention A, the vector expansion in terms of sk, scalar sk is this, and in terms of the scale, the potential expansion, scalar potential expansion in terms of sk will be this. So what is SI? So what is SI? The ith component of this. The ith component of this is, as you can see from here, minus I k by k sk. So after writing SI as minus I ki by I sk, we can drop the subscript k from the final expression, because that's the notation simplification that we follow, that in the final expression we do not write the subscript k. So this is for each kth component, and it is implicit that this is s is for each kth component here. Okay,